Hi everyone, this is Saptarshi again, and as part of this machine learning series, today we are going to discuss about linear regression. Now, this material is deeply influenced by Introduction to Statistical Learning using R, the ISLR series, and I have tried to, make the concept simpler in some cases and have not covered certain complexities. Okay, so let's learn linear regression today. All right, so we'll study the basics of linear regression model and we'll look at some improvements over linear regression. Now, to look at linear regression, so you have to agree that this is one of the most simple approaches of supervised learning. And as it is linear regression, the weightage is on regression. Always remember the response variable is going to be quantitative, as contrasted to classification model where it is categorical or qualitative. Now it may be naive, but still it is widely used and is a good starting point for building any regression models, right? Okay, so here let us take a case study. So an organization wants to increase their sales by increasing their media expenses in 3 channels. So basically they want to increase sales by increasing advertisement, and there are 3 channels on which they can increase their expense. One is TV, another is radio, another is newspaper. Okay, so if I look at the terminologies, then sales is our target variable, and this TV, radio, newspaper, these are all my features, attributes, predictors, regressors. So these are also called as independent variable. So different terminologies are there, and we have not mentioned the unit over here. Okay, so assume same unit for all of them. Okay, all right. So now, as we said that a model has two objectives. One is to understand the model, which is the inference side, and another was the accuracy side. So here are some of the goals which are from the inference side. So here we will first try to see, is there a relationship between advertising budget and sales? So this is an important question. So I can simply set up a linear regression problem, but maybe sales and budget are not that way related. Okay, then how strong is the relationship? Oh, if there is a relation, is the relationship strong enough? Which media contribute to sales? So are all media contributing? How accurately can we estimate the effect of each medium on sales? Because we want to find out, or we want to budget that way. How accurately can we predict future sales? And is the relationship linear? Because we are trying to fit a linear regression model, it's an important question whether the relationship is linear or not. And is there a synergy among the advertising media? Synergy means does spending in one media affects the other media? Okay, so let's see how it works. So essentially, let's start with a very simplistic model. Okay, so we'll talk about simple linear regression. Here we are trying to just fit a straight line where sales is given as beta 0 plus beta 1 into TV. Okay, it is the same equation as y equal to mx plus c. All right, and what we want to do is we want to find out the value of beta 0 and beta 1. Okay, and it turns out that beta 0 has a value of 7.03 and beta 1 has a value of 0.0475. So how to interpret this? The interpretation is that as an additional $1,000 is spent on TV advertising, then an additional unit of 47.5 is sold. So where from this 47.5 coming? It is coming from the value of beta 1. What is the significance of beta 0? The significance of beta 0 is that even if you do not spend anything on advertisement, 7 units will be sold. Okay, so that is the idea. All right. So if you fit it in any model using standard softwares, be it R, Python from the open source stack, or SPSS, SAS, it will give you typical outputs like this. Okay, so you will get the variables, so beta 0 and beta 1. Okay, you are getting the values here 7.0325 and 0.0475, which we saw in the previous slide, and it will have certain other things like standard error, t statistic, and p value. Okay, so here we will just focus little bit on p value. So this is something which is often ignored when we are trying to fit a model. Okay, so let's see. So if you remember that actually p values are associated with hypothesis. Okay, hypothesis from statistics. Okay, so in hypothesis testing, generally you have two hypotheses. One hypothesis is called as null hypothesis, and another hypothesis is called as alternative hypothesis. Okay, so basically what we are trying to tell over here is that the null hypothesis will be there is no relationship. What is the meaning of no relationship? The meaning of no relationship is beta 1 equal to 0. Okay, so let me repeat. The meaning of null hypothesis is the value of beta 1 is 0. Okay, and what p-value signifies? P-value signifies probability of the null hypothesis being true given the data that we are having. Okay, so if the data is like this is the advertisement on TV and this is the sales. What is the probability that there is no relationship? So that is the p-value. Okay. So if there is a relationship, what should be the p-value? Will it be higher or lower? Of course, it will be higher, right? And we will reject the null hypothesis when the probability is very, very low. Okay. So here if you see the p-value is very, very small. So we reject the null hypothesis that there is no relationship. Okay. So as I explained, H0 is there is no relationship between X and Y, and HA or the alternative hypothesis is there is some relationship between X and Y. Alright. So this is a little bit of refresher on the hypothesis testing part. Okay, so why do we do a hypothesis testing? So basically, let's say you want to find out average time spent by users on WhatsApp. Okay, and you cannot go and do it for the entire population, right? So what do? We take samples, and from that sample we try to find the average time spent. And the idea is, or the assumption is, that the sample mean indicate population mean. Then using the central limit theorem, we can find out that if my sample mean has a value of 3 hours, what is the probability that 95% cases it will be between, let's say, 2.5 to 3.5. Okay, because whatever is the sample mean value, you can understand that I get a value from a particular group having 3 hours of time spent in WhatsApp. I cannot say that, okay, the entire population spends this much of time. So I will have to put some kind of a confidence interval around it. Okay, and hypothesis testing is generally like that, is the sample mean equal to the population mean? Something of that sort you set up in your hypothesis testing. Okay, all right. So let us now go and check how to calculate the accuracy of a linear regression model. So this we have discussed little bit when we talked about mean square error. So this is another way of looking at it. So there are two terms which are significant here. One is called as TSS. TSS is nothing but total sum of square. So total sum of square is assumed to be the total variability that is present in the data. Okay, so if I think what is the ideal case where there is no variability? No variability will be there, that all the data have same value, and which is the mean, right? So total variability is variability of each of these observations, okay, from the mean. Okay, the n should be subscripted over here. And what is the residual sum of square? Residual sum of square is that the difference between what is the actual value and what we have predicted. Okay, so this is the difference. All right, and basically what is the difference between TSS and RSS is what the model can explain. Okay, so let me quickly again rephrase this. So total sum of square is the variability that is existing in data. Residual sum of square is the variability that the model cannot explain, because yi is the actual value and yi bar is the predicted value. Okay, so this gives us the residual. So if I take the difference between TSS minus RSS and divide by TSS, this gives in absolute term or in kind of percentage term that what is the variability that my model can express. Okay, so in this case this comes to be 0.612, which can be thought in a layman term that it explains 61.2% of the variability of the data. Okay, so let us now extend this further, where what has been done is that simple linear regression models has been fed on TV, radio and newspaper. The first one is for TV, then for radio and then for newspaper. And what we are going to check over here, we are just going to check the p-value. So you will see that for all these cases p-value is very less. Okay, so we cannot say that there is no relationship. Null hypothesis is not true. Okay, and when we say like this, then we say that this predictor is a significant predictor. Okay, so this is about simple linear regression. It can be very simply extended to multiple regression. Okay, the simple takes only one independent variable. Multiple regression will handle multiple independent variable. So here, in a general form, it can be beta 1 x1 plus beta 2 x2 up to beta p xp when there are p predictors. All right. In our case, we have only three variables. So we have TV, radio and newspaper. And this is the calculation of t statistic and p-value. So now if you see, do you see a difference? Please pay close attention. Okay, so you'll see that the p-value of newspaper has come to be 0.8599. So what is going on here? Okay, that earlier we saw all of them individually were significant. Why suddenly we are seeing that newspaper is no longer significant? Okay, so let us try to understand this particular question. Okay, all right, so let us consider a very absurd example to illustrate this point. So let's say you are running a regression on shark attacks versus ice cream sales for data collected for a given beach community over a period of time. Okay, so what you are doing is that for a particular beach you are counting the shark attacks and also counting the ice cream sales, and you are trying to fit a linear regression model. And you can of course understand that this is completely absurd, right? There cannot be any relationship between these two. Okay, but it shows a positive relationship. So what is the reason? The reason is that in reality, when there are higher temperature, more people come to visit the beach, which in turn results in more ice cream sales as well as more shark attacks. Okay, so actually there is an unobserved variable, right? Unobserved variable, which is number of people they are coming to the beach, and that is actually proportional to the ice cream and shark attack, not the other way around. Such kind of relationships are called as spurious relationship. Okay, so, before going further, I would like to tell you about correlation coefficient. So, correlation coefficient actually gives the relationship between two variables. Okay, and the measure of correlation is called as correlation coefficient, which is a value between -1 to +1. Okay, so that the direction of change is indicated by a sign. So what we mean by that is that if there is a positive relationship, so the TV sales go up, TV advertisement goes up, sales goes up, so this is positive. If it is the other way around, that you spend on advertisement but sales goes down, then it is a negative relationship. Okay, so the correlation analysis enables us to have an idea about the degree and direction. Okay, so you are getting a value between -1 to +1, which will tell you the degree, the strength of the relationship, and the sign will give you the direction. Okay, so here is a further example. Okay, where in the first one we are comparing height with weight, so you can understand there is a positive correlation. And similarly, you have TV watching per week with exam score. Probably, this TV watching example now should be replaced with mobile watching per week, but there definitely will be a negative relationship. Okay. So there are certain issues about correlation coefficient, which is what I want you to focus on. Is it always assume linear relationship? Okay, so you can try this as home, that you take a parabola y equal to x square, take different values of x, let's say -2, -1, 0, 1, 2, y square, you calculate, and you will see that if you calculate the correlation coefficient, you will get a value of 0. Okay, but y equal to x square is a perfect relationship, right? Strong functional relationship. Okay. Secondly is interpreting the value of R is difficult. Okay. So what we mean by that is that, if we compare the value of R from one domain to another domain, it is very difficult to say that whether it is comparable or not. As example, if we take from a domain of physics, okay, we will probably expect the R to have a value close to 1, because there is a perfect physical law existing. But if you try to do it in social science, you may have a value of maybe 0.2, 0.3, which may be significant. Okay. And of course, as we discussed, relationship may be accidental or due to a third unmeasured factor, which is often called as unobserved or latent factor, common to the two variables. The sharp example, right? Okay. So what we do is we find a correlation matrix. Okay, so what is a correlation matrix? So basically this gives you the correlation of each variables with the other one, and always remember that self correlation is 1. So the diagonal, if you look at, is 1 throughout. Okay, now check for the other correlations. So check between TV and radio, check between TV and newspaper, check between TV and cells, and you will also notice that the lower part of the matrix is not filled up. Okay, so why it is that? Because this is a symmetric metric. Okay, so whatever is the correlation between TV and radio is same as radio and TV, so you don't need to repeat it. Okay, and from here we are getting a good idea that TV has a more effect on cells than radio or newspaper. Okay, so TV has the most, followed by radio, followed by newspaper. Okay, but still there is a effect on newspaper. Okay, so let's now remove the additive assumption. So can I anyway fit in factors which can take this linear restriction? Okay, so we can actually add nonlinear terms as variables. As example, we have added here a term called as radio into TV. So this is just, we have multiplied these two variables, and what we are trying to here tell is, or these type of terms are called as interaction terms. Okay, so interaction terms just tells you this, that if individually I spend something on radio, individually we spend something on TV, their sales increase, but because of the combined effect also some more effect happens. Okay, so if one unit would have been spent on radio, five units would have, 5 people more have been buying the unit, and if we have spent on TV, 7 more people would have bought it. But when we combine, when we spend one on each, it is more than 12. Okay, so the interaction term actually tries to find this out. And if I run the same analysis here, you will see that TV into radio also has a significant effect. Uh, Even it has a more significant effect than radio. Okay. Now, before I move forward, I think I deserve an explanation that why there is no p-value for the newspaper. Okay, so maybe what is happening is that whatever increase is happening, it is mostly attributed to TV and radio. So when the company is changing their advertising budget, they are putting it in all the channels, right? And actually what increase is happening, because you cannot measure the effect of change in sales individually, right? So anyway the sales is increasing because you are simultaneously changing the advertising budget to TV and radio. Okay, so if some way you can compensate that effect and try to see only newspaper, then you will see that it is insignificant. Okay, so that is the idea. Okay, so not only that, the interaction term, you can also add higher order terms. Okay, so what do I mean by higher order terms? So basically this is a scattered plot where we are trying to find horsepower of a car and its relation with the mileage it gives. Okay, and you will see that, so this orange line is the most simple linear regression line, and of course it doesn't fit. Okay, and what you can do is you can take higher order of that, right? So instead of taking horsepower, you can take horsepower square, horsepower cube, and the curve now shows some kind of a non-linearity. Okay, so this gives you or allow you to have some non-linearity. Okay, so here an equation can be fed like miles per gallon is beta 0 plus beta 1 into horsepower plus beta 2 into horsepower square. So this horsepower square will be treated as a separate variable. Okay, and you will see that all of this has are significant because p-value is very, very less. Okay, so before I move forward, let me just quickly also talk about t statistic. So basically, whenever we are dealing with a p-value, we are dealing with a distribution. All right. So it can be a normal distribution, it can be a t distribution. So here we are dealing with the t statistics or t distribution. Okay. And what is standard error? Standard error can be thought as nothing but the standard deviations that we are getting from the sample statistic. So this we will further cover, but this is just for your reference. In case you are interested to know this, I will advise just focus on p-value. This will give you enough indication. Okay, so we understood that it is simple to interpret and implement, has strong assumptions like relationship is linear. Not only that, it assumes that residuals that we are getting are normally distribution. We also assume residuals are random, and we also assume that residuals are homoscedastic. So homoscedastic means that it doesn't show any trend. Okay, that wherever the advertising budget is less, the deviation is more, or there is no trend like that. Okay, so uh, here is an example of this homoscedasticity. Okay, so this is perfectly, residual is perfectly distributed over the line, whereas here is a pattern, whereas here is a pattern. Okay, all right. So this brings us to the end of this lecture, and here are some exercises what I would like you to do, and please do it, and let us know what is your understanding. Okay, so thanks a lot for watching, and we will follow up with an exercise on Python very shortly on linear regression.